So today I'll be speaking about some of our recent work on linear operator learning for linear operators that are commonly defined in certain PDE problems. And this is of relevance to this workshop because people these days generally are using machine learning tools to learn surrogates that can be later used to solve Bayesian inverse problems and lots of problems of interest in this UQ workshop. So I'll begin the talk by motivating why operator learning is important, especially in this inverse problems context. And then the bulk of my time will be spent focusing on how we are framing the supervised learning problem itself as solving an inverse problem. And we'll develop some theoretical results of convergence of the Bayesian solution that we take, both in a sense of error in the Bayesian sense, and also the sense of error in the sense of statistical learning. And then I will hopefully convince you through some numerical simulation studies that our theory is quite sharp in certain settings. And although quite simple, our theory goes quite beyond our assumptions into settings maybe more of practical relevance. So with that, we'll go ahead and get started. So the supervised operator learning problem that I'm interested in, and that a lot of people, at least in my group at Caltech and Andrew Stewart, are interested in, take the following form. So there is some unknown mapping psi dagger here. It can be potentially a nonlinear map between an input space X and an output space Y. And these are generally infinite dimensional spaces. And you can view these, for the purposes of this talk, as spaces of functions. So we are given n noisy samples, so n samples of some joint probability distribution on that input and output space. So that probability distribution is given first by a measure nu on X, where we sample some n vectors xn. And we have some output variables, yn, and they're given by the evaluation of this nonlinear map on the data xn plus some additive noise. Now this gives you a set of input-output pairs, xn's andyn's, and then one can then apply the framework of supervised learning to learn a good relationship between those inputs and outputs. So in any procedure that one takes to actually try to solve this learning problem, there do arise many sources of error, and it's quite important to quantify these error sources, especially in terms of the complexity question. So as you refine the number of data, as you refine your approximation, what is the complexity of that, and essentially what are the rates of convergence there. So there are three main sources of error. There's the estimation error, which of course comes from having a finite sample size. You don't have access to the joint measure here, the joint distribution, but you only have samples of it. That's the first one. Second, of course, is approximation error. So you might choose a class of neural networks to try to approximate this map psi dagger, or some sort of truncation of some sort of reduced basis or finite basis expansion. And you want to look at how the parameterization there, as that's refined, how the error gets better and better. And of course, discretization error, because these spaces are infinite dimensional in principle. Okay. I won't talk about, of course, how to actually find a minimizer of whatever learning problem that you formulate, for example, but that's another important source of error here. So I'll be focusing on the statistical questions today. So how much error do we require to achieve whatever desired accuracy level? And that's usually termed sample complexity in this field. So we'll be looking at the sample complexity question for learning simple linear operators, which is the first step to actually potentially, learning more about the sample complexity of this general nonlinear problem. So this work is joint with Martin de Hoop, who is a professor at Rice, Nick Kavatsky, who recently graduated with his PhD from Caltech and is starting a position at NVIDIA, and Andrew Stewart, who is a professor at Caltech. This preprint is currently on archive since last year, but the revision is hopefully coming out within 3 weeks or so, 3 to 4 weeks. Okay, so now I'm specializing to this linear setting. So we take the previous psi dagger setting and assume now that that is a linear operator psi dagger, or sorry, a linear operator L dagger. We're taking L dagger to be a map on a Hilbert space, so a map from H to H, but we don't necessarily assume that it's a bounded linear operator. So it can in general be some densely defined, unbounded linear operator. The data that we're going to take is the standard one. So we take some IID samples from our measure nu on X. We do this standard IID assumption. For the purposes of this talk, you can view nu as being a Gaussian measure, for example. So simple Gaussian measure or Gaussian process Gaussian process measure. But in general, in our paper, we relax this to sub-Gaussian measures or even distributions with heavier tails. Okay. Then we have our output variables here. We're taking the noise to be Gaussian white noise on the Hilbert space and assumed independent of those x's, the covariate variables. So this is the statistical model that we're going to be working with. And the goal is from this data, find an approximation, a statistical estimator for the map L dagger. So like I mentioned, the main point here is to try to understand the factors, the characteristics that can help us reduce the sample size requirements, so how much data you need to achieve a certain error level for learning linear operators. This is quite important these days, especially in these scientific problems where if you want to simulate or emulate some sort of PDE-based system, you're quite limited by the data, the training data you can generate, either by your computational resources, maybe at your university's computing cluster, or the experimental resources you have to generate real-world data. So any way we can actually reduce the amount of data volume is quite valuable. Additionally, although we don't claim to be able to solve inverse problems directly with our framework here, this theory does shed some light into the difficulty of directly using machine learning to solve inverse problems versus solving forward problems. That's because forward problems are generally characterized by compact operators in the nicest setting, not those like hyperbolic conservation laws that we saw in the last talk, but maybe some smoothing problems. And inverse problems correspondingly correspond to inverting those operators. So essentially corresponding to unbounded operators. So since our theory can treat both of these types of operators, it sheds some light on those questions. Okay. So I mentioned we're taking a Bayesian approach. So let's try to see how what we do can actually relate back to a standard Bayesian statistical inverse problem. So let me go ahead and start by telling you what I consider a non-parametric inverse problem. So I'm taking this following equation. So we have a vector y hat in that Hilbert space H previously, and it's given by the action of an operator k on f. F here is our unknown function, our unknown parameter in this Bayesian inverse problem. And we're adding some additive noise that's scaled. Okay, so this is the general model that is studied a lot in the Bayesian non-parametrics literature. And let me just highlight some of the characteristics so I can contrast it to our setting. So the first characteristic is that this map K is generally well, it's a general forward map. It's not really constrained, other than the fact that it's it's a map between those Hilbert spaces. Typically, it'll define. It's defined by your forward problem that you're interested in, such as mapping the initial condition to the solution at time t, for example. And if it's compact, people typically can study this problem theoretically using the singular value decomposition of the operator. You can essentially project this equation, which is equation on a Hilbert space, into a sequence space. And then you can solve the equivalent problem in the sequence space. We take a similar approach, but it's not quite the same. Okay, and so f of course here is actually a vector or a function valued unknown. In the operator case, which is actually quite different, our unknown now is a linear operator between Hilbert spaces. So L is an unknown operator. So essentially what I've done here is I've rewritten the previous data set here by like stacking all of the unknown functions into a bigger vector of functions. So that's what the yn is. And then this is given by the evaluation of some mapping, some tensor operator applied to our unknown linear operator L. And then we add the vector of white noises. So in contrast to the top level here, this kx, what I've defined as kxn, is a random forward map. So it's quite specific. It's defined by evaluating this operator L at n different locations, design points in the Hilbert space. And more generally, it's actually harder to use the SVD in this setting, because I mentioned using the SVD in the traditional setting is you can do that because you know k. And in our setting, we do know what kxn is. However, it's random. So if you take the SVD, your singular vectors are going to be random variables. They're going to be essentially the principal component analysis, the principal components of your data, more or less. And then so that, if you want to go that route, that would involve doing an additional PCA kind of based analysis, which is beyond what we're actually going to do. And of course here, like I mentioned, L now is an unknown operator that we're learning it in the Bayesian inverse problem. So that's kind of the high level. What are the kind of the main differences in our approach? But nonetheless, this is still an inverse problem. Y equals something kx applied to L plus noise. Great. So let's see now. So what do we actually do? Although we don't use the SVD of the forward map, we still take a quite simple, arguably quite simple approach, which allows us to work in a sequence space. So we're going to assume that we're working in the best case scenario where we actually know the eigenvectors of the unknown operator itself. So we're making the assumption that L dagger is given as this diagonal series expansion in some basis. And if you do that, the only thing that's left, the only uncertain part of the operator is its eigenvalues. So we're reducing this operator learning problem into an eigenvalue learning problem. It turns out it's still actually quite non-trivial to do this, and it's still quite important in understanding the full problem. Because although this is quite idealistic, it is really the best case scenario. You can't, in some sense, hope to do better than this in the fully non-diagonal setting. And so our work and this theory that we developed kind of gives like a baseline for what you can expect from doing machine learning of linear operators. And our numerical results, though, show, time permitting, will hopefully convince you that this also works beyond this simple assumption. Okay, the second assumption is just a weak link between our unknown operator and the data generating measure. I'm not going to focus too much on that. Okay, but let's see how this assumption now leads to this diagonal problem. So I mentioned we have eigenvalues we're trying to learn. So let's put a prior on those eigenvalues. So we're placing a Gaussian prior on the unknown sequence of eigenvalues, pointwise. So it's an independent product prior with a certain decay in the variance. And now the sequence model, under this assumption, by projecting onto the eigenvectors, we get this decoupled equation. So we get this sequence of output variables yjn. This is equal to some xjn's applied to our eigenvalues plus scalar white noise. Now again, here, as quite distinct from the traditional Bayesian inverse problems, these forward map variables, these xjn's, are random variables with an assumed variance decay. And these variables are actually correlated with each other. So these x1 n is correlated with x2n, so they're not independent. So this introduces some additional difficulty in this sequence set. But because we've assumed a Gaussian prior, we get some conjugacy, so it's quite easy to write down the posterior distribution in the setting on the sequence space. So we can explicitly analyze that posterior formula. Okay. So of course, yes, conjugacy and the diagonalization are quite big assumptions. So hopefully people can, hopefully we can relax that in the future. So this assumption is verifiable for certain examples. I'll come back to the EIT problem later on in this talk. But right now, here's an example where it's diagonal. So the electrical impedance tomography problem is a quite famous inverse problem, known as Calderon's problem. So on the unit disk, it looks as follows. So you have a elliptic partial differential equation for a electrical potential field, U, and there's a unknown electrical conductivity field, sigma, that you want to recover. And you're only allowed to make measurements on the boundary of this unit disk to measure the potential. And so those boundary measurements are measured by boundary operators. So either a Dirichlet-Neumann map or a Neumann to Dirichlet map. And so in this setting, the data that you have is actually operator valued. It's either one of these mappings here. And the goal then is from that operator, find the conductivity sigma inside the domain, only from boundary measurements. Okay. So to even get those operators as data in the first place, you often need to probe the system with inputs and outputs from either voltages and currents on the boundary. And then you have to generally solve some sort of regression problem to obtain a representation of this operator. And so that's where the theory we developed comes in the case that the sigma is a radial function. So it only depends on in the radial direction. Then these operators are diagonalized in a known basis. So the eigenvectors are the Fourier basis. And so then you only have to learn the eigenvalues to obtain a representation of these mappings. So we give a convergence rate for that process as an example. Okay, sure. So that's one simple example. There are other examples where the bases are known as well, and it's a similar type of approach where some sort of problem structure gives you the eigenbasis, and then the only uncertainty left is in the eigenvalues of the operator. Great. So before getting into the theoretical results, I will briefly try to describe what the error is that we're trying to measure, how we're actually quantifying the recovery of this operator from the data. So we'll take a statistical learning approach because maybe this is a little bit familiar. So we're first going to have some notion of test error. So what is the error, the prediction error of your operator that you learn? This is known as the population or expected risk. So we have working with a pretty general quadratic loss on the Hilbert space. So we take this quadratic loss, y equals y minus lx squared, and then we average that over the joint distribution. The training error will be the empirical approximation to that, and that leads to the empirical risk. So just averaging this quantity over your data set. And then we take the traditional link between Bayesian procedures and essentially Tikhonov regularization by making the link that the posterior mean of our Gaussian, so our Gaussian distribution here, is some sort of Tikhonov regularizer, which minimizes this empirical risk, plus a regularization based on the prior that we put on the problem. Okay, so under that link, we can identify the eigenvalues with the minimizer and equivalently with the operator minimizing this risk. And this leads to the following notions of error that we'll study. These are both types of generalization errors, which is a term that's thrown around a lot these days. And so the first notion of error is the test error, the excess risk. So this is given by the true risk of our posterior mean minus the true risk of the actual truth operator. And it turns out that this is equal to a kind of L2 based Bochner norm of the difference between our operator and the truth. So this is really what you would think of as some sort of test error or generalization error in machine learning, because we're averaging over the training distribution the predictions that we make. And then similarly, the generalization gap, this controls your overfitting. So this is the difference between your test error and your training error. And so it just measures the gap between those two quantities. Okay. So in our simple diagonal setting, these errors have very nice forms. So in the sequence space, this first one, the excess risk with the Bochner norm, on linear operators, it reduces really just to a weighted sequence space Hilbert-Schmidt norm on the eigenvalues. So it's this type of L2 norm, but it has this kind of negative exponent weight. So it's like a negative Sobolev norm. So it's quite a weak form of error. But this then allows us to measure the norm of unbounded operators. So even if these sequences tend to infinity, this norm could still be finite. So this is how you can measure convergence of discontinuous operators. Okay, great. So with that, we can give the first theoretical result, and I'll hopefully try to break this down because this exponent is quite complicated. So we're giving a theorem for the convergence of this Bayesian test error. So given a true operator that has an S smoothing property in some sense, it's in a prior with a P smoothing property. We have training data, so our training input functions from this measure nu have some sort of regularity or smoothness alpha. And this is relative to the eigenbasis. And we're actually doing distribution shift here. So we're actually measuring the error outside of the distribution that we trained on. So we have a new measure, nu prime, and we're assuming that the samples from that measure have a different regularity alpha prime. Under this assumption, we can write down this essentially that weak Bochner norm, where we take the difference in our predictions, we average it over this new testing distribution. We then average it over the posterior distribution, and then we average it over the random realizations of the training data. And this converges to 0 at some sort of algebraic rate under these assumptions. And so to break this down, I'll try to tell you what you need to do to reduce those sample size requirements. So how do you get a faster rate of convergence? By looking at these exponents. So the first thing you can do is, well, notice that you get faster convergence if your true operator is more smoothing. So if S gets bigger, this corresponds to a smoother outputs or smoother operator that you're trying to learn. Or the eigenvalues decay faster is another way to think about it. Then you get a faster convergence. Similarly, if you increase the smoothness of your functions that you're applying your operator to when you're testing it or you're predicting, so if these x's from this new prime are smoother, so then you also get a very good error. So that can be a little misleading in machine learning. If you test your model on very smooth functions, you might get a very good error, but that doesn't actually mean that your approximation of the true operator is good. It just means that you're testing it on very smooth functions, and the error will be very small. And most importantly is the last one. So this tells us that your training data should be very rough to get a good convergence rate. And this is actually quite contrast to what a lot of people do these days. So we need to take the smoothness of our training data to be rough. A lot of times people use these Gaussian process measures for new, and the covariance functions that are common are some that have exponential decay, like the Laplace kernel or the squared exponential kernel. The samples from those measures have infinite smoothness in the first case with the squared exponential. And so this theory tells you that you don't actually want to do that if you want to get this good convergence rate. You should take something very rough, not quite white noise, but something like Brownian motion as your data. Okay. So there are extensions to this theorem, but we won't get into that here. I will mention that we have a similar result for the generalization gap. So this is again the gap between the test error and the training error. Let's quantifying their difference. And so in this case, I'll just note that the error is dominated by some sort of traditional Monte Carlo term, which decays like n to the minus a half. But it's also there's also contribution from variance, which can be actually much smaller than n to the minus a half. So you can decay arbitrarily slowly if you don't choose these parameters alpha and p correctly. So I'll show this in some of the numerical results coming up. Okay, so let's try to verify those two main results. So here we're going to learn some diagonal operators. So we're going to verify the theoretical result. So we're going to take the operator here to be the Laplacian in just one dimension. So it's simply the second derivative operator. And then we're going to learn three different true operators. We're going to learn the second derivative itself. We're going to learn the identity map, and we're going to learn the inverse of the Laplacian. So under a Gaussian data, which is what this experiment is conducted with, let me draw the attention to this plot here, which is the main takeaway. So on the vertical axis, we're showing the test error on a log scale. And on the horizontal axis, I'm showing the sample size, the number of training pairs. You can see that as you increase the number of training pairs, the smoothing operator, the compact one, has the steepest slope, right? So it's converging faster. And as the operator becomes less and less smooth, as you become bounded and then unbounded, the convergence rate deteriorates. It gets much slower. So this is showing that we're actually quite, it's actually easier to learn compact operators than these unbounded operators. And the actual slopes here, if you're interested, they're shown in this bottom right table, and they're strictly slower than the Monte Carlo rate. So the Monte Carlo rate would be n to the minus 1 So there would be a 1 here. I mean, because we're in infinite dimensions, the rate is strictly slower. So in this case, substantially slower in some cases. And we're getting a good match with the theoretical result. So the theoretical result is in this first column, and then in parentheses are our numerical results. Great, so that's a good sign there. And this is just showing what happens when you learn these compact, unbounded, and bounded operators. The rates are actually sharp for that previous example because we have another result that shows that if the eigenvalues behave essentially like a polynomial at infinity, these are asymptotically exact, which is what this figure is showing. So this figure is showing on the vertical axis, it's showing those exponents, those very complicated fraction exponents. And I'm plotting that exponent as a function of the prior smoothness. So you can see that experimentally, which is these black dots, it's essentially perfectly matching the purple theoretical curve that we've plotted here. And so this is just showing the sharpness of the convergence rate in this particular polynomial eigenvalue setting. Okay, and similarly, this is like the generalization gap. So like training minus test error, absolute value. This is a little subtle because the noise in this finite sample regime, so the previous results are asymptotic, but of course we have to work on a finite sample on a computer. So we found that the noise actually controls the hidden constants in the big O notation. So if you have a small noise, the n to the minus 1/2 term dominates. So you can see our experimental results tend to want to have n to the minus 1/2 convergence, even though theoretically it should drop down much slower as you get to the left part of this figure. In contrast, as the noise gets very large, the constant on the other term in the big O notation gets bigger. And you can see that for this regime, we do match this small part, the lower part of the convergence rate very well with our numerics in black. But then it keeps staying on that term for a while, even though it shouldn't. And then eventually it drops back down to the correct rate of n to the minus 1/2 as you increase the prior smoothness. So that's just showing some finite sample effects, but it still shows that the theory is accurate. Okay, so in the last 5 or so minutes, I will show you what happens when we go beyond this diagonal setting to maybe like a more realistic setting where you don't know anything about the operator and you just need to learn a representation of it in a basis. So we're going to learn non-diagonal operators here. So what does this mean? This means that we don't have the eigenvectors anymore. We're just going to learn essentially a dense matrix representation of the operator. Also using a Bayesian estimator, like a posterior mean estimator, except now it's a full matrix now. It's not diagonal. So we don't have theory for this, but the results do really carry over quite strikingly. So here we're taking the similar example as the first, but now we're having the operator be divergence form with a variable coefficient. So now we don't have the eigenvectors because they depend in a quite complicated way on this coefficient function. It's a smooth coefficient function in this case. And we take the same operators. We're learning this differential operator itself, the identity operator, and the smoothing inverse of that, the smoothing operator, the inverse there. And we see the same conclusion. This compact operator, the smoothing one, has a much steeper slope on the error versus sample size plot. So it has the best sample complexity. And then as you become less and less smooth, as you become bounded or eventually unbounded for the differential operator, the convergence rates gets much more slow in that setting. In particular, I can write down what these convergence rate exponents are, but our theory doesn't tell us what the rate should be. But this is substantially slower than the Monte Carlo rate again. So this is like 0.3 or 0.4. So n to the minus 0.3 or n to the minus 0.4 convergence here. Okay, so lastly, I'll go back to this EIT example, electrical impedance tomography example. So previously I showed that if the conductivity was radial, then our theory would apply and we can apply the same stuff. But real conductivities aren't radial. So here's a model of a piecewise constant conductivity field. So it's on the unit disk, and it takes the value like 300 on the yellow parts, and takes the value I don't know, 30 or something, 10 or something on the blue parts. Okay, and so given this conductivity, we can sample boundary data of this PDE. This is what I'm showing on the right. So I'm showing some Neumann data in black. So these are these very rough functions on the back. So this is the functions on the boundary. So you can think of them as periodic. And I'm showing in red their corresponding Dirichlet data. So you have to solve the PDE with Neumann data, take the solution, and restrict it to the boundary to get these red curves. So the mapping from Neumann to Dirichlet is through the solution of the PDE itself. And from a bunch of these pairs, I'm only showing two, but from like a few hundred, we want to learn the actual Dirichlet to Neumann or the Neumann to Dirichlet map. Okay, so let's see what happens when we use smooth training data. So I mentioned using smooth training data is bad, and I'll show you that it's bad. So here, we're fixing the number of training samples just to 128, so 128 of those Dirichlet and Neumann pairs. Our training data is smooth in the sense that it has like 1.6 derivatives, for example. So it has some derivatives. The top row of this set of figures is showing the ground truth, if you will. So it's showing in these left two columns the real part and the imaginary part of the Neumann to Dirichlet map in a Fourier basis. So these are two operators, the true Neumann to Dirichlet and the real and imaginary parts. And on the right, I'm showing the real part and the imaginary part of the Dirichlet to Neumann map. So that's the Dirichlet to Neumann, which is unbounded. And then Neumann to Dirichlet is a compact operator. And on the bottom row, I'm showing what we actually learn using this fully dense posterior mean estimator. So we can see that the real part of the Neumann to Dirichlet map it does pretty well. However, in the high frequencies, which is the ring around this figure, this is in Fourier space, so in the high frequencies, you get this corruption. And similarly, for the imaginary part, it's worse. You get a lot of corruption in the higher frequencies. And it's even worse for the unbounded operator. So we would expect that to be harder to learn to begin with, but it's even more susceptible to noise. So we're learning from noisy data, and you can see that the reconstruction is just terrible for the unbounded operator here on the right. Anyway, so now let's solve the regression problem using rough data. So what happens? So now we take one less derivative. So what I have to do is actually have to completely remake all of these functions and then send them through the PDE again to get the different data set. So now we're only having 0.6 derivatives in the data. You can see that compared to the truth on the top, the reconstructions in the bottom are much better. So the Neumann to Dirichlet map essentially nails it very well. I mean, the operator norm and the Hilbert-Schmidt norm here is orders of magnitude smaller than the previous one. The errors in those norms. And then on the right, it's a similar conclusion. The imaginary part is still a little noisy here, but it still gets most of the characteristics in the center part, the low frequency regime. Okay, so a couple minutes over. So let me just conclude here. We've given some theory for learning diagonal operators. Although quite simplistic, the theoretical conclusions do seem to apply well beyond the diagonal setting to fully non-diagonal operator learning problems. And we're even beginning to see similar characteristics in a nonlinear setting as well. And so we've learned fundamental principles that actually help you reduce the required data you need to do operator learning. So this is smoothness of inputs, smoothness of outputs, and then smoothness of your test data, essentially. So with that, I'll conclude and hopefully have a minute or two for some questions. Thank you.